Take me to the frontier of particle physics today.
There's tremendous progress being made. It's such an exciting time in fundamental physics. Not only particle physics, but we said gravitational astronomy, the exploration of the force of gravity, black holes, quantum information, quantum computing, and all sorts of all that stuff is to me utterly fascinating. I think for the first time, it's probably true to say in particle physics, we don't know if there's anything else just around the corner, which is bad, but it is our duty to find things out about nature.
Have you ever wondered what really goes on behind the locked doors of the world's most advanced scientific labs? Could experiments we think are harmless actually be hiding something far more mysterious or even dangerous? What if the breakthroughs that awe the world also carry secrets we're not meant to know? Scientists have been pushing the limits of what's possible, but some claims suggest there's more happening than meets the eye.
What's going on at CERN now that the Higgs boson is discovered and the Nobel Prizes were granted? What are they doing now?
Well,
did they just close shop and go home?
No. I mean, what particle physics is, because we're talking about quantum mechanics, basically, it's statistical in the sense that you collide, what we do there is collide protons together at high energy.
Okay, so you've granted them energy so that when you collide them, you break them apart. You're basically deconstructing nature to see what residue comes out of it. Who ever thought it was a good idea to smash nature into itself?
Keep watching as we uncover the shocking truth about CERN and why some experts believe it could be putting humanity at risk.
Given that CERN, which has the Large Hadron Collider, LHC, discovered the Higgs boson, if you're going to discover more particles, presumably you have to keep sort of upgrading the system as the LHC was compared to what was there before, so that you can with ever greater force, bust into the particles and see what's lurking.
So we can't increase the energy of the LHC very easily. Or even easily, or even we can't really.
At all.
So that would be a major change to the machine. But what we can do and are doing is so-called high luminosity upgrades, which means you collide more protons together.
CERN is best known for its mission to uncover the secrets of the universe. From discovering the Higgs boson to studying the very fabric of space and time, its research has changed how we understand existence itself. But great discoveries often come with great risks. The European Council for Nuclear Research, commonly known as CERN, has been famous for its bold experiments since it was founded in the mid-1950s. Over the decades, its work has gained both admiration and concern. While its discoveries have been groundbreaking, some experiments have sparked fears about possible dangers, such as creating black holes or disrupting the very structure of reality. Now, one of CERN's most ambitious and controversial projects was the creation of the Large Hadron Collider, which officially began operating on September 10, 2008. This enormous machine stretches over 27 kilometers and uses powerful superconducting magnets, making it the largest particle accelerator in the world. It uses several accelerating devices to propel particles to incredible speeds as they race through its tunnels. Even though it cost more than $4.5 billion to build, many believe it was worth every cent. The LHC has delivered some of the most important discoveries of recent times, including the identification of the Higgs boson and several previously unknown particles. Picture this massive structure sending particles around a gigantic loop at nearly the speed of light, completing over 11,000 laps every second. It's a true feat of engineering and human creativity. The LHC generates an extremely powerful magnetic field, almost 1,000 times stronger than Earth's own magnetic field. Some people worry that such intensity could interfere with nearby electronics or even slightly affect the planet's magnetic balance. When particles reach their top speed and collide head-on, they produce bursts of energy and new particles. These collisions happen in moments so brief that most of the resulting particles disappear in fractions of a second. Special detectors around the collision sites capture every trace of these short-lived events. Sorting through the massive amount of data produced, over 15 petabytes per year, is a huge task. By 2017, CERN had stored over 200 petabytes of data, which equals around 250,000 full-length movies. But the big question is, what exactly are researchers hoping to find in all that data? During their studies, scientists noticed something strange with a certain type of quark. Quarks are the tiny particles that make up everything around us, and they come in different flavors. Some are unstable and change quickly into other particles. The beauty quark, which exists for just a tiny fraction of a second, caught researchers' attention. Normally, when a beauty quark breaks down, it should transform into lighter particles called leptons, either an electron or a muon, with equal probability. But the LHC's data showed something surprising. Beauty quarks were turning into muons about 70% of the time instead of splitting evenly. Now, this odd behavior hinted that something else might be influencing the process, possibly an unknown particle. It's like discovering an extra puzzle piece that doesn't fit the original picture. Some scientists began to wonder if this meant the existence of a new rule or interaction that changes what we know as a standard model of physics. This potential discovery could open up an entirely new understanding of how particles interact, possibly answering some of the universe's deepest questions. The idea of new physics extends beyond the standard model, which serves as a kind of blueprint for understanding how all known particles behave. While it successfully explains most of what we know about the smallest parts of nature, it still leaves gaps. The standard model describes three major forces: electromagnetism, the strong nuclear force, and the weak nuclear force, but it doesn't explain gravity or dark matter, which make up most of the universe. Recently, scientists noticed something in their data that didn't match the standard model's predictions. While odd results aren't rare in experiments with such massive data sets, this one stood out. They decided to investigate further. Their theory? There might be a completely new force at work, something they've named Z prime. This new force could be carried by an undiscovered particle. Even if it's very weak and difficult to detect, it might explain the strange behavior seen in those experiments. Researchers think this new force interacts differently with electrons and muons, though they still don't know exactly how it fits with unknown particles. If scientists manage to confirm the existence of new particles related to this force, it would be one of the biggest discoveries in physics. It could help solve major mysteries about space, dark matter, and even the role of the Higgs boson. Some physicists believe it could bring us closer to uniting all fundamental forces into a single theory, something researchers have been chasing after for decades. Elon Musk once pointed out that CERN built the most powerful particle collider in history, the Large Hadron Collider. Between 1998 and 2008, over 10,000 scientists and hundreds of laboratories from more than 100 countries contributed to its construction. The LHC sits in a 27-kilometer tunnel beneath the border of France and Switzerland, about 175 meters underground near Geneva. The first collision ever recorded there reached 3.5 tera-electron volts per beam, about 4 times more powerful than any previous record. After upgrades, that energy rose to an incredible 6.5 tera-electron volts per beam. Inside the LHC, this massive device smashes proton beams together with extreme accuracy. It can also accelerate lead-ion beams, which it does during a special 1-month run each year. During these periods, scientists test different theories in particle physics to confirm or refute their predictions. At the core of the LHC's mission is a quest to understand the true nature of the Higgs boson and to find new particles predicted by theoretical physics. Hadrons, the particles being studied, are made of quarks held together by strong forces, much like glue binding atoms and molecules. Among these hadrons are familiar particles like protons and neutrons, as well as others like pions and kaons, which were first discovered through cosmic ray experiments in the mid-20th century. The LHC makes these discoveries possible by colliding 2 streams of particles moving in opposite directions. This process helps scientists study the elusive Higgs boson, a particle linked to the Higgs field, a field that gives mass to other particles. The Higgs boson acts like a ripple in the quantum sea, similar to how waves appear in the ocean. It's unlike other fundamental particles because it doesn't carry any force. Instead, it reveals how matter itself gains mass. The Higgs boson was discovered at CERN's Large Hadron Collider during experiments by 2 major teams, ATLAS and CMS. The discovery was announced publicly on July 4, 2012. Scientists identified it through 2 rare decay patterns that gave the clearest signals. One where the Higgs boson decayed into 2 photons, and another where it transformed into a pair of Z bosons, particles responsible for one of nature's fundamental forces. However, finding the Higgs boson wasn't the end of the story. It was only the beginning. Since 2012, scientists have been studying how this particle behaves and decays in more detail. CERN's ongoing research shows that work on the Higgs boson will intensify in the coming years, especially during the LHC's third operational phase. This phase will be supported by the high luminosity upgrade, which is expected to be completed by 2029. Now, this upgrade will allow the LHC to create more particle collisions, giving scientists greater chances to discover events that don't fit the standard model of particle physics. CERN estimates that after the upgrade, the accelerator will produce around 50 to 55 million Higgs bosons each year, a major jump from the 3 million produced in 2017. This rise in production could be key in identifying different versions of the Higgs boson. Theories that go beyond the standard model suggest that there may be as many as 5 types of Higgs bosons, some of which are far rarer than the main one. But why is the Higgs boson such a big deal? Well, the Higgs field plays a crucial role, especially in the early moments after the universe began. It defines the nature of space itself, creating the vacuum where all matter exists. Without it, there would be no matter, no structure, and no mass in the smallest building blocks of the universe. If the Higgs field and its particle, the Higgs boson, didn't exist, atoms, stars, and even life itself would never have formed. People began calling the Higgs boson the God particle because it was extremely hard to find. The name became popular through the media, but it originated from scientist Leon Lederman, who jokingly called it the goddamn particle because detecting it was so difficult. When he wrote his book, he wanted to keep that title, but the publishers changed it to the God particle. Now, this caused some controversy between science and religion, but regardless of the debate, the Higgs boson and its field remain essential. Without them, nothing would have mass, no stars, no planets, and no humans. Scientists continue to study the Higgs boson for 2 major reasons. First, they want to understand the origins of the physical vacuum that fills the universe, tracing back to its earliest moments. Second, they're studying how this vacuum remains stable over time. The Higgs field has a special property. It carries a constant potential energy that affects the physical vacuum. This property plays a major role in shaping the universe as we know it. Now, researchers believe that by understanding this energy potential, they might uncover explanations for fundamental forces like electromagnetism, which acts across infinite distances, and the weak force, which operates only at very short ranges. To explore these mysteries, scientists need to study how Higgs bosons interact with each other. That means creating pairs of Higgs particles. While the Higgs boson has already explained how other particles gain mass, its own mass remains a mystery. Theoretical models don't fully account for it, leading to possible instabilities that could disrupt the physical vacuum through quantum fluctuations. Luckily, these fluctuations would take longer than the current age of the universe to cause any effect. Still, the search goes on. Scientists are looking for additional Higgs-like particles that could point to new physics and help explain how the Higgs boson's mass stays stable. Now, this effort requires massive data analysis and, ideally, even more powerful particle colliders. A decade after the discovery, hundreds of experts around the world are still dedicated to uncovering these mysteries. The Higgs boson was first proposed in 1964 and finally discovered in 2012. Many people have wondered why it took so long to find. The reasons lie in the particle's large mass and extremely short lifespan. To produce such a particle, scientists had to generate enormous amounts of energy in a very small space, requiring high-energy colliders. Once created, Higgs bosons quickly break down into smaller fragments, most of which are hard to distinguish from background noise. Detecting them required massive and complex detectors capable of analyzing billions of proton collisions to identify the rare signals of a Higgs boson. Despite CERN's scientific breakthroughs, conspiracy theories have surrounded its work. Some claim that CERN's experiments could open gateways to other dimensions, or even dangerous realms. Now, they fear that by accelerating subatomic particles at unimaginable speeds, CERN could unleash forces beyond human control. CERN has strongly denied these claims, explaining that its antimatter research aims only to expand scientific understanding, not to summon dark forces. Antimatter consists of particles that carry opposite electrical charges compared to normal matter. It plays a key role in cosmological theories like the Big Bang, where it's believed to have influenced the universe's creation. Rather than posing a threat, CERN's antimatter studies aim to deepen our understanding of existence and the origins of everything. Although antimatter is rare, it remains one of the most fascinating subjects in modern physics. At CERN, another concept has drawn public attention: the Mandela effect. This phenomenon describes how groups of people can share the same false memories about past events. Some believe that CERN's experiments could disturb our reality, possibly shifting timelines or creating alternate dimensions, leading to these collective memory differences. Conspiracy theories have also claimed that sinister activities occur at the CERN facility. One example is a 2016 leaked video that appeared to show people in cloaks performing a disturbing ritual involving a child. CERN immediately clarified that the video was staged as a prank and not an actual event. Whether further investigations took place remains uncertain. Given the scale and mystery of its research, CERN naturally attracts speculation. When scientists resumed operations in July 2022, after major upgrades, online rumors resurfaced. However, it's important to remember that CERN's work is firmly rooted in science, not myth. Instead of opening portals to other worlds, its experiments explore the fundamental workings of the universe, revealing new layers of physics we've never seen before. Recently, the Forward Search Experiment detector at the Large Hadron Collider made a groundbreaking discovery. For the first time, it detected high-energy neutrinos created by a particle collider. It identified 153 neutrino interactions with impressive precision, marking a major step forward in particle physics. Now, this discovery provides new insights into how neutrinos behave and helps scientists better understand stellar processes such as nuclear burning and supernova explosions. As researchers look forward to future discoveries, it's worth noting how much CERN has already transformed our understanding of the universe. From discovering the Higgs boson to detecting elusive neutrinos, CERN's experiments continue to expand scientific knowledge and challenge what we think we know about physics. Despite its achievements, CERN has faced public fears of catastrophic results or secret activities. But scientific evidence and expert reassurance consistently affirm that CERN's mission is to advance knowledge and benefit humanity. Its research not only deepens our understanding of the cosmos, but also drives innovation and inspires the next generation of scientists. The discoveries yet to come from CERN could reshape how we understand the universe. Whether it's uncovering the mysteries of dark matter, exploring the nature of space-time, or studying the fundamental forces of existence, CERN remains at the forefront of discovery. Scientists eagerly await what comes next, celebrating how each breakthrough pushes the limits of what we once thought possible. With every experiment, CERN moves closer to unlocking the secrets of reality itself. The precision of the Large Hadron Collider and the careful data analysis by researchers pave the way for discoveries that could redefine physics. The spirit of exploration that drives CERN stands as a symbol of curiosity and human progress, encouraging scientists and learners worldwide to keep seeking answers for the good of all. Neutrinos, tiny subatomic particles, they're everywhere. They are created in nuclear reactions, cosmic rays, and even from natural sources like potassium and bananas. Despite being abundant, they are extremely difficult to detect, earning them the nickname ghost particles. Since they were first observed in 1956, scientists have chased them relentlessly. In 2021, physicists found evidence of 6 neutrinos, but it took 2 more years to confirm their existence. Physicists have captured an elusive ghost within one of CERN's particle accelerators, revealing a hidden 4-dimensional structure that has long haunted researchers. In the superproton synchrotron, scientists were finally able to measure and quantify an invisible phenomenon capable of diverting the paths of particles, complicating experiments, and making precision beam control a challenge. Now, this mysterious structure exists in what physicists call phase space, which represents one or more states of a moving system. In this case, 4 separate states are required to fully describe it, meaning the structure is 4-dimensional. It's the result of a phenomenon known as resonance, and understanding it brings researchers closer to solving a problem that affects nearly all magnetic particle accelerators. With these resonances, what happens is that particles don't follow the exact path we want and then fly away and get lost, explained physicist Giuliano Franchetti of GSI in Germany. This causes beam degradation and makes it difficult to reach the required beam parameters. Resonance occurs when 2 systems interact in a synchronized way. Examples range from the gravitational interactions between planetary orbits to 2 tuning forks ringing together when sound waves from one trigger the other. In particle accelerators, beams are guided and accelerated by powerful magnets that generate electromagnetic fields. Any imperfections in those magnets can create resonances, forming a magnetic structure that interferes with the particle beam. Describing the behavior of particles moving through an accelerator is mathematically complex. Normally, 2 coordinates are sufficient to determine a particle's position on a flat grid. But to capture structures like these resonances, additional dimensions in phase space are required. In this case, 4 parameters are needed to map each point, making the structure difficult to visualize and understand. The researchers note that such a structure can easily elude our geometric intuition. In accelerator physics, the thinking is often in only one plane, Franchetti said. To map the resonance properly, physicists had to measure the beam across both horizontal and vertical planes. While the concept seems straightforward, it required years of research, detailed computer simulations, and careful experimentation to bring it into focus. Thanks to this work, Franchetti, along with Hannes Bartoszek and Frank Schmidt of CERN, successfully measured the magnetic anomaly for the first time. Using beam position monitors along the superproton synchrotron, they tracked roughly 3,000 particle beams, observing subtle shifts in particle positions. By noting where particles were centered or skewed, the team created a detailed map of the elusive resonance affecting the accelerator. What makes our recent finding so special is that it shows how individual particles behave in a coupled resonance, Bartoszek said. We can demonstrate that the experimental findings agree with what had been predicted based on theory and simulation. This alignment of theory, simulation, and experiment represents a major step forward in understanding particle behavior in complex accelerator environments. Resonances like this are a significant obstacle for particle physics. When particles are thrown off course, beams degrade and experiments lose precision. By quantifying the 4D structure, researchers hope to develop strategies to reduce beam degradation and maintain the high-quality beams needed for current and future experiments. The next step for the beam is to create a theoretical framework describing how individual particles respond to an accelerator resonance. This framework could provide new tools for controlling particle motion and improving the performance of magnetic accelerators worldwide. By mitigating the effects of these resonances, scientists can achieve the stable, precise beams required for experiments ranging from basic physics research to particle collision studies. The discovery underscores both the complexity and the ingenuity involved in modern accelerator physics. Mapping a 4D resonance is not something that can be done intuitively. It requires careful measurement, sophisticated modeling, and a willingness to approach the problem from multiple angles. By achieving this, the researchers have opened the door to new ways of thinking about particle motion and control in high-energy accelerators. The study, recently published in Nature Physics, highlights the combination of theoretical predictions, advanced simulations, and experimental validation. It demonstrates that even phenomena that seem invisible or abstract, like this 4-dimensional ghost, can be captured and analyzed with the right approach. Physicists have long known that resonances could interfere with particle beams, but until now, such structures were largely theoretical. Observing the 4D resonance directly confirms that these effects exist in real-world accelerators and that they behave as predicted. This knowledge allows researchers to refine accelerator design and operation, improving beam stability and precision. Now let's take a look at some mysterious clips that prove something strange is going on in the world. You don't see something like this every day, a building that seems to channel lightning directly into itself. In the viral clip, the bolts didn't scatter across the sky as usual. Instead, they bent toward a glowing pole, almost as if the structure was drawing them in. The uploader claimed that this took place on a secluded island, and that's when the theories began. Some viewers said it resembled Tesla's idea for unlimited energy. Others believed it was proof of secret technology that's already perfected, but hidden from the public. Whatever the truth may be, the scene felt less like a science fiction movie and more like a glimpse of forbidden science in action. People are used to neon lights and occasional grid failures, but this event was nothing like that. A sudden flash turned the entire sky bright blue, followed by complete darkness just seconds later. The phenomenon had no connection to local power systems or weather activity. It was something entirely different. Soon after, rumors began spreading. Some claimed it was an alien ship briefly decloaking, bending light to hide its form. That instant of total blackness that followed, Well, many believe it was the exact moment the craft slipped out of sight, or maybe even out of reality itself. What happened that night remains a mystery that no one has ever been able to explain. Imagine standing by your window for a quiet night of stargazing, and suddenly spotting a column of light rising from the forest. That's exactly what one local captured on camera. The beam climbed upward, ending with a faint bluish pulse glowing against the night sky. As he watched, he felt an eerie sense that something was cloaked above, possibly a ship concealing itself. But another thought crossed his mind. What if it wasn't just a beam, but an entryway? If that's the case, then something might have already stepped through it and quietly merged into our world. At first glance, it looked like a distant storm. A deep electric blue light flickered across the horizon, lighting up the clouds as if the sky itself were alive. Someone recorded the scene, and the footage quickly went viral. Officials offered the standard explanation, a transformer explosion. But many online didn't buy it. It was too bright, too consistent, and too controlled to be that simple. Some theorists suggest it might have been a failed experiment, or even a test of some kind of portal technology. Whether you believe the official report or not, one thing was clear: that glow didn't look natural at all. It was raining when a man walked down the railway tracks in 2020, and that's when he saw something he couldn't explain. Out of nowhere, a glowing blue orb of energy rolled along the rails, sizzling and sparking as if it carried its own storm inside. It moved smoothly without slowing, crossed the track, and drifted into the forest before disappearing completely. Witnesses had no answers. Some said it was a rare electrical event, while others claimed it wasn't natural at all. Maybe a probe of unknown origin quietly surveying the area before vanishing once more. So, what are your thoughts on these mysteries and discoveries? Let us know in the comments below, and subscribe to our channel for more content.